Good day, everybody. This is Mr. Wright. We're going to start talking about the chapter 20, which is on page 383 of your book. If you're dyslexic, that's page 383. If you're vertically dyslexic, that's page E8E. This is all about gas pressure and atmospheric pressure. And if we want to measure pressure, we're going to use this formula P equals the air pressure plus whatever you're measuring with. So this P here, this little teeny p, is actually a rho. It stands for the density of the object. And G stands for gravity, and H stands for the height of that. And the instrument we use to measure atmospheric pressure is called a barometer. It's a big tube of mercury that you see down here in the lower left-hand corner that I'm pointing to with the red arrow here. And the way this works, and I'm going to have you draw this on the quiz, the weather quiz that you're going to take on the next class period, is you got a tub of mercury. So we've got this mercury as a liquid metal. It's very, 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 very dense, very heavy. And inside that is a tube that goes like this, okay? And as the air pressure pushes down, we use green for the air pressure here, as it pushes down, then it pushes the mercury up the tube, okay? So the mercury gets pushed up the tube. Most of the time, the height of that mercury is about 76 centimeters or 0.76 meters. So if I want to know air pressure, I'm going to use that formula up there of P equals the original pressure plus P GH. Well, the density of mercury, that weird looking P, that I just put across square around, that is 13.6 kilograms per cubic meter, times gravity, which is 9.8, times the height of it. Well, if it's 0.76 meters, I'm going to put that in there. And this all ends up equaling 1.013 times 10 to the fifth newtons over square meters, or what we also call 1 atmosphere. Now, here's the number we're going to use a lot in the gas law equations. And whenever you talk about atmospheric pressure, we're just going to say 101.3 kilopascals, or you could say 101,300 pascals. So either one of those, we're just going to get used to those numbers. That's one of those you're going to have to memorize and just sort of know as we go along. Now, let's continue on here. Something that you might want to know about atmospheric pressure and air is that it weighs a lot. And most of our atmosphere is within the first, I would say, 5 kilometers or about 3 miles of the Earth. And that gives you about 50% there. Then you go up to 10 kilometers. That gives you about 75% of the atmosphere. 20 kilometers, you're all the way up to 90. So the air gets a lot thinner as you go up. But air weighs a lot. If you take the air just in this desk where my camera sits, that's about a cubic meter. That weighs about, let's see here. That weighs about 1.29 kilograms, or I would say almost 3 pounds. So it's quite heavy. If you were to take, everybody just look right on top of your thumb, okay? That's a square inch. If you would go and take all the air that's on top of your thumb and go all the way up to the atmosphere, that would weigh about 14 pounds. So 14 point something pounds per square inch. That's a lot of weight that's on top of you. But you got to remember, pressure not only pushes down, it also pushes up. And that's why you don't feel it as much as you think it does. The other thing that's cool about atmospheric pressure is that it only pushes. In other words, science never sucks. It only blows. So if you look at atmospheric pressure pushing down on a straw, for instance, okay? The way straws work is by this little picture down here. You can see that this lady is sucking up water through a straw. And what happens is the water comes down, or the air comes down, goes into your drink, pushes down on the water or whatever you're drinking, and then it pushes up the straw. So once again, air pressure is pushing, it's not sucking. If I were to completely put a rubber stopper in your drink like so, and you were to try to suck up the water through the straw, you couldn't do it because no air can get into the drink to push down on it. So that also talks about how we pump water up. The highest you can actually pump water up with any type of pump whatsoever is 10.3 meters. So let's say I'm trying to create a vacuum and I got a great big hill here. So here I am on a cliff. This is me up here trying to pump some water up the hill. Okay? And down here I have a little lake that I'm trying to get the water out of. And here's a great big tube. I'm going to suck that lake out. Okay? We got to remember the way we get air up is for the air to come down, it pushes on the river, and then the air pressure pushes the water up the pipe. Okay? Well, the air weight at 10.3 meters, sorry about that, let's try this, the atmospheric air weight equals the water weight at 10.3 meters. So therefore, the highest I can pump anything up to the very, very top is 10.3 meters. And that's why we have these great big tanks or these water towers that we have. You might have seen them. Sometimes they look like great big mushrooms. See? This great big thing with the water up here. So we pump the water up to this tower. As the water falls, it gets pressure to the other houses that are 10.3 meters higher than the river, and then we can pump it up to the next hill. So once again, the highest you can pump anything up is 10.3 meters with a vacuum pump. Okay. Now, let's go into weather now. There's going to be a little quiz about the weather, and I'm also going to make sure that you write some of this stuff down. That's how I'm going to check your notes. So this is a little bit strange here. You would think that wet air would be heavier than dry air, but it's not. If you look at most of our air, I think about 78% of it is made out of nitrogen, which is N2. I think 21% is oxygen, which is O2. What would you think about that? If you now substitute one of those molecules for water, let's take a look at this. N has an atomic mass of 14, but you got two of them. So that means each molecule weighs about 28, or each mole weighs about 28 grams. Oxygen is what, 16? You got two of those, so each molecule would weigh about 32 grams. Well, let's look at water. If you were to replace this with water, water is H2O. Well, two H's are 1 gram apiece, plus the oxygen, which is 16 grams, that only gives you 18 grams total. You see how this is lighter than the dry air? So you start replacing water molecules with N2 and O2, the air becomes a lot lighter. So therefore, moist air has less pressure. And that way we can sort of start predicting the rain or predicting the weather based on the barometric pressure. If you have high readings, you're going to have really, really, really nice weather. Okay, it's clear and sunny. If you have really low barometric pressure, that means you're going to have some rain coming through. So let me take a look at some of these maps here and discuss this. Here is a big map with a bunch of lines on it. These lines are called isobars. And what these green lines do, the green lines connect areas of similar pressure. So all those lines that are connected there have all equal pressure. Now the other weird thing though is that different lines have different pressures. So lines that are really close together mean that the pressure is changing fast. And that usually means it's going to be very, very windy and often stormy. So if you look at Kentucky over here, Kentucky has high pressure. You see that blue H that I'm circling here? And there's Kentucky right there. Well, high pressure means we're going to have sunny, it's going to be calm. But if you look out here to the west, where we get most of our weather from, here is this thing called a front. And so you'll see this line with a bunch of blue arrows. I'm circling right here. And it has a bunch of L's around it. Well, that means low pressure. So you've got a low pressure front come through. That means there's going to be storms all around that line. Okay. So if you look up here in the northwest, way up here by Canada and Alaska, got a huge, huge storm system, almost like a big hurricane brewing up there. It's not really a hurricane, but it's a bad, bad storm system up there. And usually, once again, it just comes sweeping across and affects our weather. And if I were going to predict this weather, I would look, well, you look at Kentucky right today. Today would be sunny because there's high pressure. Now, if you look out to about the Midwest, that's where we're going to get our weather tomorrow. So I'm going to put a great big blue star right here. Okay? So tomorrow, I would say we're going to have, I just spelled that wrong, that's horrible. Anyway, I would say that's going to be also sunny because you have high pressure. But in about 2 days from now, if you notice this front right here, depending on how fast it's going, okay, I would say the next day, the third day out, we're probably going to have rain because you have a low pressure, a low front coming through. Okay? And so that's what meteorologists sort of do. They look at the fronts coming across the United States from the west, and they sort of estimate how much it's going to affect us. If you look at this next map down here, let's try to predict, this is what you're going to do on the quiz. Today, so if you look at today's map, we have a high pressure right over top of us, so I would say it's going to be sunny. Probably in the 70s based on the color code there. Okay. Once again, because you have high pressure. And if you notice, right out here through the front, so I'd say early tomorrow, okay, so it's tomorrow, so you're going to have rain, because you've got a front coming through. And if you look out to the west of that, it turns color, so I'd say probably in the 60s. Okay. After the front comes through, you got a high pressure, so the third day out, with high pressure coming through, you predict sun. So, and then if you look out past that, you got another little front coming through. So the third, fourth day, I would say, hey, we're probably going to have rain again. So it's going to be on and off rain and sun for the next days based on this map here. Okay? So that's how you predict the weather going on. Now, the next thing I want to discuss is all the things with flow of gases or flow of fluids. And there's an equation that sort of explains how a garden hose works. You know, if you just have the water coming out of the garden hose, so here's a little green garden hose here. Okay? Let's just say that that garden hose has, I don't know, a little area here of 1 square inch. Okay? And you have, I don't know, 10 liters of water coming out of that per minute, whatever you want to do. Okay? So that's the velocity of it coming out. Well, if you look at these formulas here, you have AV equals AB. Now, here's what I mean. The first AV has to equal the second AV. You say, what the heck does AV stand for? Well, A is going to be your area, and V is going to stand for the volume or the velocity of the water coming out. So let's take a gander at what would happen here. Let's see if I had an area of 1 square inch, and I'm going to multiply that by 10, I'm going to say meters per second, something like that, instead of liters per second. Let's do meters per second. And I'm going to have to stop here because my smartboard just locked up. Okay, let's see what would happen now if you put your hand over the hose. So now I'm going to take my big old thumb and put it over the garden hose, and I'm going to make that area now a lot smaller. Okay, so now let's make the area, let's say 1/10 of a square inch. Okay, making a real teeny hole now. I want to know what has to happen to the second velocity. Well, if you divide both sides now by 1/10, now this velocity ends up being 100 meters per second. So that's really flying. Okay? So once again, it says as the area goes down, your velocity's got to go up. And that's why you make a garden hose go a lot farther, you make the area smaller. Okay? So pretty simple formula there. Now let's get into, since we're pretty close to spring break, and a lot of you will be flying over spring break, how come airplanes fly? This is something called Bernoulli's principle. And as the velocity of a fluid increases, the pressure decreases. Now, your brain's going to be thinking one thing, but you got to sort of look at another. So as that garden hose, as you put your thumb over the top of it, or you take the nozzle and you turn it down, doesn't the pressure against the sides of the garden hose increase? So as the speed goes down, the speed of the fluid goes down, because you're turning off the nozzle, then the pressure goes up on the sides. But if you let the speed go out through the nozzle, then the pressure on the sides of the garden hose goes down. Well, the same thing happens with an airplane. So I'm going to draw an airplane wing here. And airplane wings are sort of curved on top and flat on the bottom. So they sort of look like this. Well, when the airplane wing goes through the air, the top goes at the same speed as the bottom. You don't have the top flying off and the bottom flying off. So therefore, the air, since the top part is going through at the same time as the bottom part, the air on top is faster because it has a longer distance to go. You see that curved line here? This curve is much, much longer than the bottom part that is straight. So that means the air on top has to go faster. Air on the bottom, slower. Well, let's read Bernoulli's principle. It says as airspeed goes up, pressure decreases. It also says as airspeed goes down, goes slower, that means pressure increases. Well, if you have high pressure on the bottom and low pressure on the top, the high pressure is going to push into the low pressure, and all of a sudden you now get lift. And that's how an airplane flies. So when I got on the airplane last spring break, and I was all nervous about flying, as the airplane went through the daggone air, we started to go up. I just stood up and I said, "Yeah, Bernoulli!" I just knew he could do it. So that's how that works. Okay, let's go to curveballs. All you baseball fans out there, discuss how curveballs curve. I'm drawing me a nice little baseball here. And the baseball has threads in it like so. And when a pitcher throws a curveball or a sinker or whatever, he actually rotates or spins the ball. We'll actually do this in class. Okay? And as he spins the ball's rotating here clockwise, but the ball is going this way. And so the air goes over top of it, up here like so, and it also goes on the bottom like so. If you notice, the threads are going to push the air backwards on top. So you have slower air on top because the threads are pushing that air back. Let's say threads push the air. Okay, backwards, okay? Well, on the bottom, the threads are pushing the air forward. So here you have faster air. Think about Bernoulli's principle here. If you have faster air, that means lower pressure. If you have slower air, that means high pressure. High pressure always pushes into low pressure. So what's that ball going to do as it goes through the air? It's going to get pushed down, and so now you have a sinker. If I throw the ball and spin it sideways, so the ball is spinning not over the top like you see in the picture, but in and out of the board. Let's say it's now spinning sideways like this. I don't know how to make that happen. But anyway, you would now get a curveball. Okay, so you got curveballs, breaking balls, and that's how a pitcher will spin a ball. Okay. Hope this helps with the gas pressure. We'll go into the gas laws on the next video, so make sure you watch that one too and take all the good notes. Love ya. Bye.